Welcome back to the course entitled Elementary Electrochemistry. In this course, in the previous lecture, we have discussed about the ionic conductivities and based on the limiting ion conductivities for different ions and then the corresponding limiting conductivity of the electrolyte, that is the equivalent limiting conductivity or equivalent conductivity at conductance at infinite dilution. We have discussed how one can calculate the value of equivalent conductance at infinite dilution for some unknown electrolyte which may be strong or a weak electrolyte. So in today's lecture, I am going to discuss about the ionic mobilities. In terms of ion conductivities. The velocity at which an ion moves under a potential gradient of 1 volt per centimeter in a solution is called the ionic mobility of an ion. The limiting value of ionic mobility is obtained when the solution is at infinite dilution. So one can write that L0 cation is equal to some constant K into U, and L0 anion is equal to the same constant K into V, where U and V are the speeds of the cation and the anion at infinite dilution, right. So the lambda 0 is nothing but L0C plus L0A. So it is nothing but K into U plus V. This is what we have seen in the previous class. Now let us take a solution of an electrolyte of concentration C under complete dissociation that is near to infinite dilution. And use 1 cubic centimeter of this solution between 2 electrodes kept at 1 centimeter apart, and of area 1 centimeter square. Further, a potential difference of 1 volt per centimeter is applied. So, what we know from our previous equations is that lambda 0 is equal to L into 1000 by C, or simply L is equal to C by 1000 into lambda 0 is nothing but L0C plus L0A, correct? So, now if I is the amount of current passed through the solution, then I equal to E by R, which is equal to E into lambda, where lambda is equal to 1 by R, correct? So, now one can further simplify I equal to E into L as capital lambda becomes equal to L when small l, that is the path length, is equal to 1 centimeter and the area of the cross section is 1 centimeter square. This equality is a numerical equality, that is, these values are same, but the units are different, if you have remember. Now, in this case E is equal to 1 volt per centimeter. So, therefore, one can write L I equal to L once again the values are same. Do not confuse that the unit of L and I are same. So, I, if it is ampere, so Ls, whatever the value of Ls, it is in ampere, right. So, now one can further write that I equal to L, which is nothing but C by 1000 into L0 C plus L0 A, or simply equal to C by 1000 into K into U plus V. Let us take this equation as equation number 1, right. We have written this from the previous page, which is here. Now, the total gram equivalent of ions transported by this current I to the two electrodes per second is given by U into C by 1000 into 1, that is the 1 volt per second, and V into C by 1000 into 1. So, that is equal to C by 1000 into U plus V. Now, since 1 gram equivalent of ions carry F Faraday, or rather 1 Faraday of electricity, 1 Faraday of electricity, so total charge carried per second is I equal to C by 1000 into U plus V into F. This is the equation number 2. So, now we see that equation number 1 and 2 has same quantity on the left hand side. So, one can equate this equation 1 and 2 and write the following: C by 1000 into K U plus V, which is equal to C by 1000 F U plus V, which essentially means that the value of K is nothing but F, that is the quantity of electricity passed in coulombs. Therefore, one can write L0C equal to F into U, L0A equal to F into V. So, therefore, you can write U equal to L0C by F, V equal to L0A by F, right, and then one can further replace this L0s by transport numbers. U equal to T plus at infinite dilution into lambda 0 by F, and V equal to T minus at infinite dilution into lambda 0 by F. So, the speed of the ions at infinite dilution can be determined using their transport numbers at infinite dilution and the corresponding lambda 0 of the electrolytes. Right? So, the the value of ion conductivity depends on certainly on the transport number of the ions, and the transport number further depends on the concentration and transport number depends on the temperature as well. So what happens is the ionic conductivities, that is L0C or L0A, depends on temperature. So based on several experimental determinations of ion conductivities of various ions, we have arrived at an empirical equation for the dependence of L0 at or on different temperatures. On temperature. What is the relationship? L0 or rather LT 0 is equal to L 25 degree C 0 multiplied by 1 plus 0.02 multiplied by T minus 25, where T is the temperature in degree centigrade unit. This is an empirical relationship which has been arrived at based on various experimental data for the ion conductances of a particular ion at different temperatures. So, you do the experiment at various temperatures. T maybe this T can be 0 degree centigrade, 10 degree centigrade, 20 degree centigrade, like that, 30 degree centigrade, and you measure some 5 to 6 experiments at 5 to 6 different temperatures, and based on the trends of those values of L0 at all these temperatures, this equation can be arrived at. So, with this I will be giving you a few problems to solve based on the topics which we have learnt in last couple of classes. So, the first problem is the following. Given the equivalent conductances of sodium sodium acetate, sodium chloride, and HCl as 83, 127 and 426 in mho centimeter square unit at 25 degree centigrade, respectively. Calculate the equivalent conductance of acetic acid at infinite dilution. This is a straightforward question from the lecture that we have delivered already in the previous class. Calculate the ionic mobility of cation in a 0.1 molar solution of NaCl at 25° centigrade, given that T plus is equal to 0.39 and lambda 0 for NaCl is 127 mho centimeter square. And the third problem is the following: at 18° centigrade, the mobilities of ammonium and ClO4 minus ions are 6.6 into 10 to the power minus 4 and 5.7 into 10 to the power minus 4 centimeter square per volt per second. Calculate the equivalent conductance of ammonium perchlorate and the transport numbers of the ions. Right? You see here the unit of the mobility is given here. So, you have to take care of the unit while doing any calculation related to electrochemistry. Rather, you should keep in mind about the unit calculation for all the physical chemistry related problems, because the physical quantities come with their correct appropriate unit. Any calculation without indicating their unit is meaningless. Therefore, I would emphasize that you should get yourself associated with the units of various physical quantities that we are discussing in this course, because when you write your final examination, marks will not be awarded if the units are not correct. So, we will stop here at this point and we will continue in the next lecture discussing about some of the applications of conductance measurements. Thank you.